Welcome to the Deep Dive, where we really get into the research that's changing things. And today, wow, we're looking at something the International Energy Agency calls the new king of power generation. That's solar photovoltaics, PV. I mean, the growth is just, it's explosive globally. It's reshaping energy as we know it.
It really is. And a big part of that picture involves these horizontal single-axis tracking systems, HSAT for short.
Right, those big solar farms where the panels tilt to follow the sun.
Exactly. And their market share is climbing fast, maybe 30% now in big utility projects, but projections show it hitting 40% by 2030.
And maybe even 60% by 2050 if things are really cost
And that's
optimized.
the potential, yeah.
But okay, even kings have their challenges, right?
Yeah.
And for HSAT, a big one is this mutual shading, one row blocking the sun for the next one. And here's the kicker we're diving into today, the way we've usually dealt with this. This deep dive suggests it might be, well, totally outdated. Okay, let's unpack this.
Yeah, absolutely. And the study we're really digging into today spells it out perfectly in its title. Impact of backtracking strategies on techno-economics of horizontal single-axis tracking solar photovoltaic power plants.
Whoa, okay, that's a title.
It is, but it's spot on. Basically, backtracking is this technique. It's pretty clever, actually. The panels adjust their tilt, not just for the sun, but to avoid shading each other. The goal is always maximizing energy capture.
So this backtracking,
Yeah.
what was this study really trying to figure out? Just avoiding shadows, or is there more to it?
Oh, it's definitely more nuanced. The core mission here was to get a much better handle on how different ways of doing backtracking affect, well, two key things. First, the technical performance, how much electricity you actually generate. And second, the economic viability, basically how much that electricity costs.
Makes sense.
And crucially, this study focused on the modern half-cell modules, because those are everywhere now. The ultimate goal, find the best way to plan and run these HVAC systems going forward.
Okay, let's visualize that shading problem again. You've got these long rows of panels, and if they're packed too tightly, especially like early morning or late afternoon when the sun's low, one row casts a shadow right onto the next one. Pretty intuitive, really.
Exactly. And that shadow, it's not just, a visual thing. It's a real problem. It directly cuts down the energy yield. And worse, it can actually cause these damaging hot spots on the modules, degrades them over time.
Ouch. Okay.
So historically, the answer was, well, standard backtracking, STD. The panels just deliberately move away from the perfect sun angle, just enough to avoid any shadow.
Seems logical, right? No shadow, no problem.
That was the thinking. But here's where the study throws a curveball. It suggests that the standard backtracking, this avoid all shadows rule, it might actually not be the best thing for today's panels.
Wait, how can avoiding shadows be bad?
It sounds completely counterintuitive, doesn't it?
Right.
But there's a really important reason. These half-cell modules, they make up something like 90% of the market now. They're the standard.
Right.
And the fascinating thing is, they behave differently when they're partially shaded compared to the older full-cell types. They're often more tolerant. They actually perform better sometimes when, say, the bottom half is shaded horizontally.
Ah, okay. So they can handle a bit of shade better.
Yeah, exactly. And because of that tolerance, this rigid, no shadow ever approach of standard backtracking, it might force the panels into angles that are actually worse overall.
Worse how?
Well, you lose energy in other ways, like from what are called incidence angle modifier losses, IAM losses. That's basically light reflecting off the panel because it's hitting at a really shallow angle, an angle the standard backtracking forced it into just to avoid that tiny bit of shade.
Got it. So if standard backtracking isn't the magic bullet, what did this study look at instead? You mentioned 4 strategies.
That's right. 4 different approaches, sort of like different philosophies for moving the panels intelligently. Let's quickly run through them. First, NO. That's no backtracking. It's the baseline. Panels just follow the sun as best they can within their tilt limits, usually plus or minus 50 degrees. Ignores shading completely. Simplest, fastest algorithm.
Okay, the just track the sun method.
Pretty much. Then you have STD, standard backtracking, the traditional way we just talked about. It checks for shade, and if it sees any, it tilts back maybe 1 degree at a time until the shade is gone. Computationally pretty fast, too.
The avoid all shade method.
Then comes ADV, advanced backtracking. This one changes the goal. It's not just about avoiding shade. It prioritizes the total amount of light hitting the module, the total irradiance.
Okay, so it might accept some shade if the overall light is better.
Potentially, yeah.
Yeah.
It lowers the tilt only if doing that improves the total light. It doesn't explicitly calculate shading or those IAM losses, but it can still help, especially on cloudy days with lots of diffuse light. Speed-wise, it's fast to medium.
Interesting. And the last one?
The last one is ADVS, Advanced Sophisticated Backtracking. This is the most complex one. It basically simulates the light hitting the panel for all the possible angles between true tracking and flat
Wow, okay.
to find the single best angle that gives the highest total irradiance. And crucially, this one does account for both shading losses and those IAM losses. It's aiming for the absolute global optimum.
So it's doing the most work computationally.
Exactly. It takes the longest to compute.
Okay, maybe an analogy helps here, like
Yeah.
driving somewhere.
Yeah, that works. Think of NO as just, driving straight there, ignoring Waze, or Google Maps, ignoring traffic.
Right?
STD is like taking this huge detour just to avoid any possibility of traffic, even if it's just one slow car. You avoid the traffic, but the detour takes way longer.
Makes sense.
ADV is maybe like quickly glancing at your GPS. Is this route slightly better right now, just based on current conditions? Maybe avoiding a sudden jam, but not recalculating the whole trip.
Yeah.
And ADVS, that's the full recalculation. Your GPS checking every single possible route, considering all the traffic, accidents, road closures, everything, to find the absolute fastest arrival time, even if the route looks weird. It's optimizing the outcome, which here is energy yield.
Great analogy. That really clarifies the different approaches. So how do they test these strategies in this study?
Well, they simulated a pretty standard HSAT system using components you can actually buy specific tracker, specific half-cell modules.
Like real-world stuff.
Exactly. They used a two-in-portrait setup, or 2P. That just means two panels stacked vertically on the tracker. It's good for packing more power into less space, better ground cover ratio.
Okay. And where did they run these simulations? Just one place?
Oh, no, this is key. They went global.
Hmm.
9 really diverse test sites. We're talking subarctic places like Lippinranta in Finland and Watson Lake in Canada,
Wow, cold.
all the way to hot deserts like Ouarzazate in Morocco, Jaisalmer in India, Tet in Mozambique, plus tropical spots, moderate climates, the works.
So a huge range of conditions. Sun, clouds, temperature.
Exactly. That makes the findings much more robust, more widely applicable. You're not just looking at perfect sunshine scenarios.
And I assume the modeling was pretty detailed.
Oh, yeah. Hourly resolution for the whole year, super detailed dynamic analysis, and they validated their model against well-known software like PVSys to make sure it was accurate. It was a very rigorous setup.
Okay, sounds solid. So let's get to the juicy part, the results. What happened with the energy yield? You mentioned full load hours, FLH.
Right, FLH, basically how much energy you get out over the year relative to the system's peak capacity. And here it is, that really counterintuitive finding we talked about. STD, the standard avoid all shade method, often performed worse than NO, backtracking the method that ignores shade completely, especially when the rows were closer together.
Worse? How much worse?
Well, it depends on the site and spacing, but the trend was clear. Why? Because forcing the panels flat just to avoid a little bit of morning or evening shade, it meant they were at a terrible angle for capturing the main sunlight for longer periods. Those reflection losses, the IAM losses, they added up and outweighed the benefit of avoiding the shade, especially with those shade-tolerant half cells.
So doing less, just tracking the sun and ignoring shade was actually better sometimes than the standard fix? That's wild.
It really is. Now, compare that to the others. ADV, the simpler advanced method, showed small but generally consistent improvements over NO. Maybe not dramatic, but positive.
Okay. And the sophisticated one, ADVS.
ADVS. That one consistently delivered significant improvements in FLH, on average over 1% better than NO. But in some cases, like for a 6-meter row spacing in Munich, Germany, it hit a 5.3% improvement. That's a lot of extra energy.
Wow, over 5% is huge in this game.
It really is. And looking at shading losses specifically, STD, yeah, it eliminated them. Zero shading loss, just like it's supposed to. But as we saw, at the cost of overall yield.
Right, the trade-off.
Whereas ADVS, it didn't aim for zero shade. It strategically reduced shading losses by about half compared to NO. It accepted some shade when the trade-off for a better overall panel angle was worth it. It's about optimizing the net result.
So ADVS is playing chess while STD is playing checkers, kind of.
Maybe. It's definitely making more complex calculations about the best move, yeah.
Okay, so we know ADVS gets more energy. What does that look like in terms of how the panels actually move day to day? How different are the tracking patterns?
That's a great question, and the tracking angle profiles really show the difference. Let's take those examples again. Lappeenranta, Finland, high seasonality.
Right. Big difference between summer and winter sun paths.
And Tet, Mozambique, low seasonality, near the equator.
Sun path more consistent year-round.
Okay, so NO is simple. It just follows the sun until it hits the till limit, then stays there. STD, you clearly see it in the mornings and evenings. The panels go nearly flat, way off the ideal sun angle, just to dodge shadows. Then they snap to the limit during midday, then flatten again.
Very distinct pattern.
Yeah. ADV is interesting. On cloudy days, you might see it keeping the panels at lower angles than NO or SPD. It's optimizing for that diffuse light from the clouds, not just the direct beam.
Or
And then ADVS. It's the most dynamic. You might see it stay at higher angles than STD right after sunrise or before sunset, accepting some shade, because the direct sunlight on the unshaded part is so strong at that better angle that it wins out.
so it tolerates shade when the sun is intense and the angle game is big.
Exactly. But then at other times, maybe mid-morning or late afternoon when the sun is lower but shadows are longer, it will apply significant backtracking, similar to STD, because then avoiding the shade is the better move overall. It's constantly calculating that optimal balance.
Fascinating. Much more complex behavior.
For sure. And near the equator, like in Tet, the whole backtracking period is shorter because the sun rises and sets faster, so the differences are less pronounced. But the ADVS logic still finds gains.
Okay, this all leads to the big question. Money. What does this mean for the cost of the electricity generated? The levelized cost of electricity, LCOE.
Right, LCOE. The ultimate bottom line for energy projects. It tells you the average cost to produce each kilowatt hour over the plant's lifetime.
What did this study find about LCOE?
This is probably the most impactful finding. That STD backtracking strategy, it resulted in higher LCOE compared to NO backtracking in most scenarios.
Higher, so the standard method actually makes the electricity more expensive.
Yes, significantly so in some cases. Up in those northern places, Lappeenranta and Watson Lake, with tight row spacing, the LCOE was up to like 8.7% to 9.0% higher with STD compared to just letting the panels track the sun and ignore shade.
9% higher cost just from using the standard shading avoidance. That's incredible.
It's a huge economic penalty for rigidly avoiding all shade. It proves that intuition was wrong, at least for these modern modules.
Okay, so STD is bad for the wallet. What about the others? ADV.
ADV showed modest LCOE reductions. Good, better than NO, maybe up to 1.2% lower cost. So, heading in the right direction.
And the sophisticated one, ADVS.
ADVS. The clear winner again. It consistently delivered the lowest LCOE. Compared to NO, it lowered cost by up to 5.0%, like in Munich.
5% lower cost is pretty good.
It is. But compare ADVS to STD, the traditional method, that's where it gets really dramatic. ADVS achieved up to 12.0% lower LCOE in Watson Lake and nearly as much, 11.7% in Lappeenranta.
12%. That's massive.
It's enormous. Even closer to the equator, like in Tet, ADVS still delivered significant savings, up to 6.6% lower LCOE than STD.
So what does that mean practically for someone planning a solar farm?
It's huge. It means using a strategy like ADVS lets you do one of two things. Either produce electricity at a significantly lower cost, making solar even more competitive,
Right.
or you could choose to space the rows closer together, packing more power into the same land area while maintaining a competitive LCOE. That's critical where land is expensive or just unavailable. It really changes the design possibilities.
Well, so what's fascinating here is this isn't just about, a tiny tweak. It feels like it's fundamentally rethinking how we optimize these massive solar farms. A seemingly small detail has huge ripples.
Absolutely. This study just underscores how these operational details, things that might seem minor, like which backtracking algorithm you choose, can have a really profound impact on the long-term technical and economic performance. And that's, well, vital for planning our energy future.
Where does this go next? What are the implications looking forward?
Well, a big one is extending this kind of analysis to the next wave of technology, especially bifacial modules.
The ones that collect light from both sides.
Exactly. They're projected to be like 70–80% of the market by 2030. How these backtracking strategies interact with light hitting the back of the panel is a whole new layer of complexity. And there are other new cell designs too, like third or quarter cells. We need to understand optimization for those as well.
And moving from simulation to reality. You mentioned ADVS takes longer to compute.
Right. For real-time control in a power plant, doing these complex hour-by-hour simulations might be too slow. So the next step is likely developing more sophisticated, maybe equation-based algorithms that capture the essence of ADVS but run much faster.
Like maybe sensors on a few test rows feeding data into a central controller,
That's exactly the kind of thing people are looking at. Real-time data feeding faster, smarter algorithms to optimize constantly.
which really leads to a big question, doesn't it?
It does. How quickly can we actually get these advanced, optimized strategies implemented out there in the field in operating power plants? The potential is clear. Now it's about bridging that gap to really unlock everything solar PV can do.
So this deep dive really hammered home that managing these trackers isn't just about following the sun blindly or sticking to old rules. It's about intelligent, dynamic adaptation.
Precisely. This study shows pretty definitively that standard backtracking is often outperformed, and that these more sophisticated yield optimizing strategies like ADVS are really key to maximizing both the energy we get and the economic value, especially with the modern half-cell panels that dominate the market now. It's a crucial insight for anyone planning or operating these systems.
And that was our deep dive into the impact of backtracking strategies on technoeconomics of horizontal single-axis tracking solar photovoltaic power plants. Quite a journey. So here's something to think about. If tweaking something seemingly as minor as how a solar panel tilts can lead to double-digit cost reductions, what other hidden optimizations are lurking in the technologies we use every single day, just waiting for us to find them? Something to chew on. Until next time on the Deep Dive.